what I would call a computational scientist does all day. I think it is useful because it's a pretty new discipline, and it a lot of times it doesn't have an academic home in only one department. The beautiful part about Rice is that we do have an academic home for this kind of activity in computational and applied math. So what I wanted to do is to look at a few problems that I've worked on to try to give you an idea how what I do is different from the other people that I collaborate with on the project. And I can't, if you give me a couple more hours, I can explain all of the problems in depth. But since I don't have that, I'll just try to give you a feel for the problem, and I'll try to be very specific about the part that I was contributing to. So one thing that I thought it was neat at the beginning, here's a set of people, all of which I've collaborated with, and all of which I've collaborated with for a number of years. And I would consider all these people to be computational scientists in this kind of nomenclature. And the interesting thing is, if you look, here are the degrees that they all received. So it's a mix of math, computer science, engineering, geophysics, and I didn't think to make the slide, but what you would see is if I listed all the departments that they're in, they're again all different: math, computer science, engineering, and the degree which they received bears almost no resemblance to the department that they're actually employed by now. And so it lets you know that this is a new and evolving discipline, and I think will continue to evolve rapidly even in the next decade. So I thought I would give an idea of the kind of contributions that we try to make in computational science. And the first topic I'm going to look at is accuracy of computation. And this is pretty traditional. And I think when most people think of people who do numerical analysis or algorithms like I do, that we contribute to the accuracy of computations. And so I want to give an example of that. But there are other more nebulous, at least right now, contributions that we make to the generality and the ease of use of computing. And that's what I want to look at in the second diagram. And then I want to talk about what I think is an underserved part of computational science, namely the scholarship aspect. So let me talk about a problem that I've worked on for maybe almost 10 years now. And that is the problem of simulating the conduction of ions down biological ion channels. So ion channels are the way that your body runs itself. For the most part, with a few exceptions, the electrical parts of the body do not use electrons. So we are very different from your electronic devices in that we use ions, because ions are big and fat and easily contained and channeled compared to electrons, which are very tiny and weigh almost nothing. And so we were interested, my collaborators here, Bob Eisenberg, Dirk Gillespie, at Rush University Medical Center, we were interested in simulating these systems because this explains how your heart beats, how your muscles contract, even how nerve impulses are shuttled down your nerves. And so it's a very fundamental system. And in my mind, there hadn't been a good physical description. There was a good structural description of these ion channels in many cases, but the physical description was lagging behind. And so we have a simple model here where the ion channel confines some ions. Here, the red are oxygens, which are tethered in the channel, and then the green and blue are, say, sodium and potassium or sodium and calcium ions that might try to percolate through. And even a model as simplistic as this one can give you valuable physical insights and is non-trivial to really calculate with. So the kinds of outputs we're trying to give are shown here, sort of chemical potentials and maybe densities of the species. So the density of potassium here shows that this is an equilibrium calculation. So it shows that there's really nothing in the center of the channel. So potassium is not flowing through. So this is a channel that selects for calcium. So there's not much penetration, and the Hartsfer chemical potential shows you the reason that potassium is not making it through this channel is this tremendous potential that it would have to make it through. So it's an entropic effect rather than an electrostatic effect, which was the question we were trying to answer here. So we use a tool called classical density functional theory. Most people that think of density functional theory think of the quantum analog, which people use to describe all sorts of atoms and molecules. But the classical analog is when you're dealing with things that do not need a quantum description. Electrons tend to need a quantum description. They're so light, they're so fast. But ions, as I said, are fat and slow, and so they're very well described by the classical equations. And so a classical density functional theory is a very good tool for understanding inhomogeneous fluids with different components. So what a density functional theory means is that I have a functional, this omega, which is going to give me information about different things in the fluid. This is called the grand canonical potential, but it's not that important right now. What is important is that it's only a function here of the concentrations of each species, nothing else. And there's a famous paper by David Merman where he basically says under very weak assumptions you can always do this. And so that's a nice formulation because now we know we can get everything we want by having unknowns that are just the concentrations of our ionic species. And that's a minimization problem. So here we're just going to find the Euler-Lagrange equations for this. I'm going to talk today only about an equilibrium formulation. You can do out of equilibrium formulations using like a Nernst-Planck formulation here too, but it just makes it a lot longer to explain. So it's much easier to go over just the equilibrium. And the wonderful things about DFT is that it computes what you want to know, namely ensemble average quantities, and it computes them with the resolution that you want, namely very, very fine resolution in space, angstroms, the size of atoms, but physical resolution in time, microseconds. A big problem with today's computation in molecular electrostatics is that you have tools like molecular dynamics. Molecular dynamics has very fine resolution in space, but also in time, like femtoseconds in time. So you're needing billions and trillions of time steps to say anything meaningful. And in fact, on any kind of molecular dynamics calculation for an ion channel of this kind, you might have one or two ions traverse the ion channel in your entire computation. So there's no idea of getting statistics. And if you think that that might not be important, it is important because in your body, everything having to do with conduction is regulated by the pH, by the concentration of ions outside of your cells, let's say. And that concentration, if it changes by, 1 part in 1,000 or something like that, that can kill you. That's why if you don't have enough Gatorade, your body will stop working, right? You need this ionic concentration, and it's impossible for MD to predict anything like that because the kind of statistics you would need to tell the difference between the two concentrations of ions outside a cell is unapproachable in the current computing that we have. So it's only with these kind of effective models that we can answer questions like this. And the beautiful thing about this DFT work is that we could not only agree with experimental results, but there's a beautiful paper by my collaborator Dirk Gillespie where they predict experimental results, which is something that I just don't think you ever see in this area with molecular dynamics or anything of that sort. And that's because you can't approach these timescales. So I just want to give a quick introduction that shows you what I'm talking about mathematically, just so you can get an idea. In equilibrium, what it says, the definition of equilibrium is that the chemical potential is not fluctuating, right? It's reached its steady state, so the gradient is zero. Let's have an equivalent thing that says the chemical potential is equal to what you would get in a bath, what you'd get in an infinite homogeneous medium. you can divide the actual chemical potential into parts, the part that arises from just the ideal gas behavior, the randomness, a part that arises from external things like walls, and a part that arises from interactions not taken into account by the other two pieces. This is usually called the extra chemical potential, so EX. The ideal gas part is well known, and just arises from the entropy of an ideal gas. If you rearrange, you can write this as an equation which determines rho from these other pieces. This extra piece of the chemical potential we're going to divide into contributions that arise from the fact that ions are hard spheres, they're balls that knock into each other. So many popular models do not take this into account, say the Poisson-Boltzmann model. The Poisson-Boltzmann model assumes pointwise interactions, which is great for electrons, but bad for ions, because much of what goes on with ions is due to crowding. And we'll see that the ion channel I'm looking at is something like a basketball hoop, in that if you took two of the generic ions, two calcium ions, they would fit side by side just about in the channel, just like two basketballs fit in a hoop. So there's a lot going on with hard sphere interaction. There are also long-range electrostatic forces, long and short range, I should say, electrostatic forces, and so you have another electrostatic part here, so hard sphere and electrostatic. And then you can divide the electrostatic into a mean potential, this phi, and then some short-range interactions, which we'll call screening. So short-range electrostatic and the overall mean field electrostatic. And the mean field electrostatic obeys the Poisson equation. Pretty standard. Now, describing hard spheres, chemical potential is where most of the involved mathematics is. And here is the model from Rosenfeld. This is called the fundamental measure theory model. And really, let me try to give you a high-level understanding of what's happening. What's happening is we derive the chemical potential as from a grand potential phi. This is a standard kind of argument. But we use a specific basis, these bases of these vectors n, which are especially adapted. And I'm going to describe the n's. And then we use these weight functions. And the idea is that you cannot make accurate predictions by imposing a pointwise equation of state here. You have to have integration. I'll try to give an idea of why that is later. So these potentials phi, their form comes from certain limiting arguments. What if 3D approaches 2D and then that approaches 1D? Or what happens if things get very cold and you start to freeze and form a crystal-like thing? And so this has occupied a whole branch of physics, but we take these results, and what you tend to argue is that in the limit of a continuum, these reproduce certain equations of state. So if you are familiar with the fluids, this particular thing reproduces the Carnahan-Starling equation of state. But of course, you can write other functionals and they will reproduce other equations of state. So the basis that we write this in these n's, and this is why it's called fundamental measure theory, is just a bunch of averages of the concentrations. So you can see we have a sum over species here, and we average the concentration of each species with a certain window function omega, and here are some functions. So for instance, we average over a ball, or then we have a repeated average just weighted differently, and we average over the surface of the ball, and we have a directionally weighted average over the surface of a ball. So it's these kind of geometric averages that we're dealing with, and it turns out to be a really nice basis for expressing these things. And what you might notice here, the form of this integral is suggestive. The form is a convolution. And we can, in fact, cast all of those different weight function integrals as convolutions because they're all either even or odd, and so you can flip the signs and make it the entire integral a convolution. And the beautiful thing about convolutions, and many people know this, not just computational people, is that they look particularly simple in what's called frequency space. If we if we Fourier transform the whole thing, what we can do is the convolution of rho and omega can be calculated as the pointwise product of their Fourier transforms, and then you take the inverse transform to get back to get n. So this is wonderful in the sense that we have very fast algorithms for the Fourier transform and its inverse, normally called fast Fourier transform algorithms, which are not only have a good scaling, not only they're n log n, and if I have n variables, it takes nearly linear time to do it, but they also have very, very small constant, which is not true of other linear algorithms like the fast multipole, which has a big constant. So it's a beautiful algorithm in a lot of ways. And in fact, if you look back to the hard sphere integral I said as well, that can also be cast as a convolution for this this functional and the weight function. So this seems great, and this is where I entered the project. The people said, we think we know how to do this. There's these convolutions. We have our 1D code working. We'd like to go to 3D. How about that? And I said, this sounds great. And that's when I got involved. The problem is that you start off with these things and they sound good, and then you get to you get to one of the hang-ups, and this is where having a solid knowledge of the underlying mathematics and the computational end of the mathematics is very useful. So those integrals that we use the convolution theorem on, the convolution theorem has some prerequisites, and you have to pay attention. So one of the prerequisites happens to be that everything needs to be sufficiently regular or sufficiently smooth. And if you looked at the weight functions, they're not. They're like weight 1 over a ball and then nothing. So there's a jump at the surface of the ball, or if it's just on the surface, there's a jump as we pass to the from inside to outside. So these are not smooth weight functions. And if you just take an FFT package and run it on these, FFT packages have an embedded assumption that this regular quadrature that they're based on works. And a regular quadrature will be okay in 1D for these problems, but in 3D, the errors can be what I'll call O1. So they can be 100% error in your answer, and there's really no way to cope with that without going back to the more basic mathematics. In addition, even if it's not 100% error, it's still sizable, and it destroys your conservation property, like conservation of mass, which is very important for these chemical reactions. You can't be creating ions out of nothing. So what do you do? So the insight that we'll use, and this is not a new idea, but it was a new application of an old idea, is that these functions, these window functions, are not smooth. They have jumps, but their Fourier transforms are smooth. So what went wrong? It's not that that the non-smoothness itself kills us. It's that the fast Fourier transform of it was inaccurate, and because it is the fast Fourier transform assumes that the function input to it is sufficiently smooth. So what do? Well, we do the Fourier transforms of the window functions by hand. Then those functions are smooth, and we multiply them by the presumably smooth densities. We're usually not dealing with shocks in the ionic density or anything like that, so that's okay. And then we can use a fast Fourier transform back because the thing now multiplied by the smooth rho is sufficiently smooth. In this way, we get the whole thing to work. So all the hard work was merely doing these integrals analytically. And this is where sometimes the chain of software breaks down. We think that we've solved the problem and we produce some software and we plug the libraries together, but sometimes the implicit assumptions behind the library aren't noticed. And so we might want to augment, for instance, the FFT libraries with some of these symbolic capabilities. I think, like if you plug those directly into Mathematica, it doesn't work right. But if you kind of manipulate them a little bit, it will be able to give you these answers. And so we plug this in and do that, and that gives us, it's almost enough to give us an accurate result. There's also another problem. If you notice the last term in that canonical potential for hard spheres has this form, 1 minus these two unit vectors over their square. This, you can prove that this quantity is always less than 1, but you have geometric errors representing curved boundaries, and those geometric errors can give you nonsensical negative numbers for this term. And so what we did is, instead of getting higher order surface representations, which would be very, very costly in 3D, we just explicitly enforced this bound. And the reason is that you don't need terribly accurate evaluations of this quantity far from the answer. All we're doing is using it to generate search directions so that you can have descent to the solution of your nonlinear equations. Once you're close to the answer, you don't have this problem, you never violate this bound, and therefore it's a decent strategy to just enforce the bound explicitly. It could conceivably decrease the convergence rate of our nonlinear iteration, but we didn't see that behavior. So there were two parts. There was a hard sphere part. So we solved their problem with the hard sphere interaction. They've got a similar kind of expression for the electrostatic interaction, namely that you have some kind of a potential and you integrate it against density. Here we're going to say the C's are 2-point correlation function, or the Green's function, and the psi's are your perturbation away from the, we'll say the 2-point correlation function is good for the bath, but you have a perturbation away from that because you introduce walls and channel walls and stuff. And so you have this full form, and then integrate against density differences. And you can solve this exactly in the bath, in the mean field case, where you have no walls, no channel, just and you get what's called a screening parameter, which means sort of the radius around a particle that it takes for its electric field to die off due to all the other water particles screening it out, or other ions screening it out. And what we do is we just approximate this kernel. Instead of using the exact answer for the mean field case plus a perturbation, we can just approximate the whole thing with Taylor series. And this is kind of what is done in this field all over the place. You can see we use 3 Taylor terms. And they're in terms of these screening parameters, which is the right way to expand it, because these are the small quantities. So if you put this in, it's also a convolution. So we can, in fact, it's really beautiful because we only need to do one inverse transform each iteration, because these things are constant, unlike our densities in the last integrals, which are fluctuating. So it's really a great scheme for this, except the FFTs are also inaccurate for these expressions. And so what we can do is we can do the analytical Fourier transforms again here. We can write actually a general expression for the analytic transform for any Taylor term. We just use 3 here, but in the paper we have the expression for any one of them. And so we're able to use pretty simple numerical ideas to solve problems for these for this computation, which allowed them to compute very large 3D systems and get actual laboratory predictions. So I'd say this was an unqualified success, and it showed the usefulness of what we do in numerics. Now, that's beautiful, and it's traditionally what we do, but I think there's a larger class of things that we do. So I want to try to show in the next example that we can be very effective even if we're not sticking to the making things more accurate script. So what about making things more general? So an awful lot of time and money and computing cycles is invested in solving PDEs. And so I do a lot of this. So traditional PDE codes, however, are written such that you choose a discretization, you choose a way to solve it, and you code everything up. So it's very, very difficult to compare different discretizations. I don't even know of a code that can compare finite volume and finite element, for instance. But even comparing very similar elements is often not done. Not to mention comparing different meshes. How does simplicial compare with hexahedral, compare with polyhedral? What about being able to run 1D and 2D and 3D problems in the same code? It's a big problem, because the way we should be judging algorithms is what is the cost per digit of accuracy? And very often what you see in a paper is not a cost per digit of accuracy and a comparison between algorithms. It's just a description of the algorithm that was used, which is not nearly as valuable for the reader. I mean, the real point of computational science papers should be, I want to provide enough information so that my reader can make an informed decision about the algorithm that would be best for their problem. And I think too often that doesn't happen. So I'll say why I think the interfaces at at the intersection of the meshes and solvers are not done in the correct way. Yeah. So I use lots of different languages. I think the best pure language for scientific computing today is unquestionably C. But we use a lot of Python to wrap C and to do data analysis. I think I'm pretty hopeful about Julia, but I don't think it's mature enough to really. I would never write a library in it right now. And I don't see the point of writing in Fortran. It's still really behind the capabilities of C. If you like it, that's okay. It's easy to interoperate with, and we do interoperate with Fortran libraries. I just wouldn't write new code in it because of the drawbacks. And I think C++ is needlessly overwrought and provides little value to the user and imposes huge costs. So very simply, that's in a nutshell, that's what I think. The traditional interfaces between solvers and meshes, I think in one sense, they're too general. You just throw to the solver a matrix and a vector, and you don't really tell them much about the mesh that it came from or the discretization. So the solver doesn't know that there's several fields here and that they're blocked, or that there's saddle point structure, or that you know the near null spaces and stuff like that. But in another sense, very often, they're too specific in the sense that when you write the assembly code that makes a matrix or a vector, you write it so that it can only do it in one dimension, with only one cell shape and with only one kind of discretization. And you make explicit references in the code to things like vertices and edges. And there's no good interface for things like transitive closure, which kind of percolate up over all the dimensions. And this is the kind of problem that when you get into, I'd like to do several different elements with one code, or I'd like to do finite element and finite volume in one code, or I'd like to compare 1D and 2D and 3D. How do you do it? Do you just write separate code for everything? And that is what has been done in a couple of these larger packages. I would argue that's what's done in Deal and Trilinos. And so we're going to try to show a different way of thinking about this, where you can unify a lot of these ideas. So instead of representing a mesh as, say, an explicit list of vertices that are connected to edges, and those edges are connected to faces, and those faces are connected to cells, let's think about a mesh in a more general way. It turns out a mesh can be represented, and when I say mesh, I mean a very general thing, what's called a CW complex for the mathematical people. It can be represented as a graph, and that's a very neat idea, because a graph is really just a representation of a single relation. So I don't need to know all the specifics of vertices and edges and faces. I can just live with a graph. And I can discover everything else I want to know about the mesh from that graph, like dimensions and adjacencies and everything like that. And I can do traversals, and I can calculate sizes. And so it seems too good to be true. So what I want to do up front is show you some examples. So imagine that you have this very simple mesh of two triangles. And I want to represent the triangles and the edges and the vertices. And so I've numbered them all up, and I've used colors to indicate the different kinds of mesh pieces. And what you can see below is that I have a graph that represents the mesh, in the sense that if you look at vertex 7, it's attached to two edges, 2 and 3. And so here are there are arrows to 2 and 3, and the same with all the other vertices. And then the 2 and 3 have arrows to 0 because they are edges of that face. It turns out that the mesh above and the graph below are isomorphic. If you just give me the graph, I can reconstruct the mesh, and if you just give me the mesh, I can generate the graph. And in fact, they're even isomorphic if I take away the edges. This is still something where I can go between the graph and the mesh interchangeably. And this was known to mathematicians for a long, long time. It's been known at least since the 1920s, and I think before that. And so you might say, well, does it only work for simplices? No, you can do it for quadrilaterals here in the same way. And you can also take away parts of the mesh and it still works. Does it only work in 2D? No, it works in 3D. And in fact, do you need to mark out what kind of node everything is? For instance, do I need to color these nodes blue here that are edges? And the answer is no. You can give me the generic graph, and I can infer from the graph that there are blue nodes and which ones are blue, and I know that they correspond to edges. So it's true that every piece of information in the mesh is also in the graph, except every topological piece of information. The geometry, of course, is not, but that's a small thing to keep separately. In fact, when you're talking about solving PDEs on these, you want to represent the PDE solution as a function over the mesh. Well, that's the same way you represent geometry, as a function over the mesh. The geometry should not be embedded in the mesh data structure itself, because the mesh data structure is really only topological. You shouldn't pollute it with that kind of geometric information. So, this is, to sum up, we have this very, very general and very, very simple representation of all meshes. So we can put any mesh we would get into a simulation, we can put in this format. So not only is it a way to represent them, but it's a way to canonicalize them. So I can read any mesh format and convert it to this, and this is how PETSI works, is I can read in all these formats and I convert it to this, and then I can use that and write it back out in a different format. So even if you just wanted to convert one mesh format to another, this is a great idea. But this also allows us to compute in different ways over the mesh. So this is a great mesh representation, but if it wasn't matched by very generic operations, if I had to write separate code for everything I wanted to do, then it wouldn't be very useful. But it turns out that everything I want to do can be formulated as simple graph operations, and I want to try to show you that here. One of the easiest things to ask is, if I'm a face, what are my edges? And what you see is that this is the same question as asking, what are the in-edges to this node representing the face? And see, the in-edges here are 2, 3, and 4. And this is what we'll call a cone. And this kind of terminology comes out of combinatorial topology, which is why it seems a little strange. If I wanted to ask the related question for the vertex, what edges come into the vertex, this is the graph query of what are the out edges. So here it's 3, 4, and 6. And so this is, you can think of this as the dual operation, and the way we get the graph dual is to reverse all the arrows. So if we reverse the arrows, this is the cone, right? But now the nice thing is that if you represent things this way, then the questions about closures become very simple. Like, what if instead of asking, if I have a face, what are my edges? If you ask, what's everything on my boundary? Well, I have these edges, 2, 3, and 4, but then I can follow their arrows up to 7, 8, and 9. And it's a very, very simple graph query. It's the transitive closure of this relation in the graph. Whereas if I coded them separately, I'd have to say, well, first take all of the edges on my face, and then take all of the vertices on those edges. If I had 3D, then I would have to put another part in and say, well, first I want the faces on the cells, then I want the edges on the faces, then I want the vertices on the edges. But here I just have one kind of thing. I just follow the arrows up. I don't care what the points represent. And so writing the code is quite a bit clearer and much, much more general. You can also make you can also turn around and do the dual operation. Now, if I say not just every edge that goes into this vertex, but also the faces that are seen by those edges, then I can just keep following these arrows down like I do here. And that's what we'll call the star. And I will show you there's other graph operations like the meet, the intersection of the two sets. So if I follow arrows up, the intersection of those arrows for here can tell you things like what divides two cells, what edge divides two cells. Well, that's the meet. I could turn the query around. What do these two points border a common thing? Like do 8 and 9, the vertices border a common edge? 4, yes, they do. If I had 7 and 9, I would follow the arrows down and say, no, they don't. Or they border a common cell, but not a face, right? So these are exactly the kinds of questions that you ask when you're writing a PDE code. And so just to get more specific, I'd like to give you as complete an example as I can of doing PDEs this way. So if we consider, I'll just write an expression. This is a simple expression for a PDE weak form. And what I'll say is, look, here's the test function phi and its gradient. And then I'll just say there are functions f0 and f1 which define my physics, which I stick in here. And these are just pointwise functions. And this is just the discrete form of this where I introduce some quadrature. And what this is sufficient to represent most problems that I'm interested in. It's not doesn't totally cover everything, but I can tell you how to do, I think, most anything with this and with how to fix it up if it doesn't cover it already. And I'm going to show you as completely as I can that in code, you don't need to know anything about the mesh except that graph idea. So you put your boundary conditions in your vector if you have Dirichlet boundary conditions, and I just won't go into that as much, but it follows the same way as everything else. But how do we do our little element integrals? Well, here we say, get me all of the roots in the graph. It doesn't matter whether it's 3D, 2D, 1D, whether these are squares or pentagons or whatever. They just have to be roots. They have to have no out edges. So I get the no out edges and I loop over them. And then here's the one time where I need to know about geometry. I need to compute the geometry of each of these cells. How is it done? Well, I ask for the transitive closure of the cell, which gives me everything on its boundary. And then from the boundary, I can compute the geometry. So that does depend on what kind of cell it is, but nothing that comes after does. So I have one point where I calculate the geometry, and it's never involved again. So it's orthogonalization of concerns. Then I could say, get me all of the information that's on the closure of this cell. So, temperature, pressure, whatever you're solving for. So this doesn't depend on what shape it is, and it doesn't depend on what dimension it's in. It just gets me all that, and for each cell I store that. Then I do my integrals, and then after I'm done integrating on each individual cell, then I take that information in the element vector and put it back in the closure. Again, it's totally independent of what kind of mesh I have here and what kind of discretization. So you may say, well, maybe everything's hidden in that integration routine. So let me show you the integration routine. So the integration routine, it says, give me some fields and a quadrature and a set of coefficients that I get from the closure and geometric information, and I will give you the residuals out again. So I loop over these elements, and I loop over the quadrature points. So I loop over elements and quadrature points, and then for each quadrature point, I give a location, and I can just get that from the geometric information. And for each then for each field, for each basis function, I loop over. Well, what this set of code does is give me the pointwise values of the fields and their gradients. So whatever reconstruction you're using will happen here. And this is just the finite element reconstruction. And it doesn't depend on what the element is. It's just tabulated. It's just tabulated basis and the coefficients that you got. And so I can do, this will work for any finite element. For finite volumes, this also works if your tabulated basis just represents the cell average, right? So you can make this structure work for a very wide range of discretizations. I won't say every, I guess, but all the ones I care about. And right here, then, I'm showing that you do between here and here, you have to transform the derivative to real space. That's a simple thing. It's just you have to keep track of what spatial coordinates you're in. Then once you have made the coordinates and the field values and the gradients at the quadrature points, then you just call these pointwise functions, f0 and f1. But the pointwise functions don't know about the discretization. They don't know about the mesh. They just know about the values at points. And once you have them, those values, you weight them in using the geometric information here, the determinant and the quadrature weights. And then once that's done, you just do synthesis. You use the basis tabulation and the pointwise values. And again, this works for a wide range of discretizations. This is very independent code. And you'll notice that this integration code works in any dimension. So I didn't write special code for 1D or 2D or 3D. It's not special code for triangles or tets or quadrilaterals or pentagons. They will all work with this one code. And the beautiful part of that is now, not only do I not have to rewrite for those things, but optimization becomes much simpler because you have one routine that does this integration. So what with my friends Andy Terrell, who is now in industry, and Karl Rupp at Technical University of Vienna, we rewrote this one routine, FEM Integrate Residual Batch, which is maybe 200 lines long at the most. We rewrote it for the GPU, so we split it into kernels. But because we only had to optimize that one routine, we were able to get optimized GPU code that runs on 2D, 3D, triangles, quadrilaterals. It doesn't matter. It works, so I don't have to keep re-optimizing for every different thing. And it achieves very high performance. So we got maybe 350 gigaflops, which if you do the computational model for this stuff, it's all bandwidth limited. And that's really, within 10% of the peak you can possibly get, we estimate. And so we have some papers on that. And I think, when we get new hardware, newer than GPUs, we'll get the Knights Landing from Intel any day now. This is going to be very valuable because you're going to be only optimizing this one very central kernel for all these different methods. So, as I said at the beginning, there were these problems with the way traditional PDE codes were constructed. You couldn't compare different discretizations. Well, now I've done it with Andy, but other people have done it using this method. This is the group from University of Oslo, comparing very sophisticated HDiv and HCurl element methods. You can compare different mesh types. So I'm one of the principals on this pilot software for earthquake simulation. And you can compare 1D, 2D, 3D. You can compare TETs with hexes and a lot of different things. And as I said, same thing. And there are now, here's one of the papers I have, but here's a paper that's not even me, that's enabled optimal solvers on these things without extra programming. You can do them all with options in PETSI without recoding anything because there's enough information passed from the mesh to the solver. Okay, so I know I'm running close to time. So let me just say, I wanted to say a little bit about scholarship in computational science. In mathematics, the perfect vehicle for communication is the paper, and it's been established over hundreds of years. If someone writes a proof down, you can immediately use that proof. There's nothing else for them to tell you. However, with computation, if you write an algorithm down, there's a lot more to tell that's not in your algorithm. And really, the right way to communicate that is not the paper, but the numerical library. And we've been producing numerical libraries now for about 45 years. I would say, the first real numerical library was the Handbook for Automatic Computation at ETH in 1970. So I am part of a group of people who develop a library called, or a set of libraries called PETSI for the scalable solution of nonlinear algebraic equations, usually from PDEs or boundary integral equations. So I've worked there for a long time. I am responsible for the parts of PETSI that do unstructured grids, and here's what I showed you on the left, but there's also coarsening algorithms that I think are pretty cool. I'm responsible for a large part of the composable nonlinear solver setup, and we just had a paper in SciEM Review about that. I put all of the support for finite elements in here. Here is a representation of the 2010 Christchurch earthquake in New Zealand, and here's some more earthquake volumetric representations. This is just slip on the fault. And I also did a large part of the GPU optimization and optimizations for other kinds of accelerator hardware. And what I would say is that it was a very valuable activity for us to dedicate time to producing a community library that's used by tens of thousands of people. And we do get many citations each year, and it really has helped my career academically. And I would say, if you look across time, this is how the real computational leaders work. I would say, I'm in a department of applied mathematics, and I look at applied mathematics as sort of the bridge between the mathematics and the science and engineering. And I think if you look at guys, say, take Euler, he was very inspired by physical problems and could be considered as much of a physicist as a mathematician. But in particular, if you look at the slide rule was invented well before Euler. It was invented by Napier in the 1690s. But when Euler gets a hold of it, 2 decades later, he takes the concept of the logarithm, he relates it to the exponential, which had not been done before, analytically in a power series, and uses it to solve a wide variety of analysis problems. So here, the computation is fertilizing the mathematics in a way we don't think about too often. And again, most people know von Neumann and Norbert Wiener, but they don't talk about Kantorovich. Kantorovich is famous for his wonderful functional analysis book, for providing perhaps the first real proof about the convergence of Newton's method. But he was also head of the parallel computing library at St. Petersburg and was well ahead of the Americans in using parallel computing. He was using parallel computing in the 50s to tabulate special functions much faster than the Mark, which was a better computer, but he wasn't running in parallel. And so he, I think, was very forward-thinking for the time. And today we have machines here with billions of processing elements, and we have high-quality numerical libraries that let you, in a day or a week, build something that might have taken someone a lifetime to build a couple of decades ago. And this is just going to lead to more scientific discovery if we figure out how to mesh correctly with the mathematics community, with the science and engineering community. All right. Thank you very much. I'd be happy to answer your questions. I know it's 2 o'clock, but sorry for running right to the end of time. Oh, well, I mean, I don't think it's easy to say that one part is more important than another part. Um, I would say the following. In my own work, I have always been tempted to push the complications to the analytic side and to keep the meshing as simple as I can because the complication that comes from meshing tends to be combinatorial and really difficult to get around. Whereas if your complication is analytic, there's a lot of space for approximation and things. And so I always feel that my efforts are better spent in the analytical side than the kind of geometric combinatorial side. Oh, well, I think the secret to collaboration, any collaboration, in particular this collaboration between mathematics and say biology, is that you have to have enough respect to learn something about the discipline. So in my work, I might spend a year or something learning about the problems, you're learning what people have done because it's not enough to hear a problem and say, well, we in physics have worked on that or we in math have worked on that and here's our solution because a lot of times with a problem like a biological problem, they've thought of a lot of things. And the reason the problem's hard is the particulars, the details that you don't know about initially that cause it to be hard and cause the solution most people know not to work. And so in my experience, it's more about people willing to give up some of their mind, to give up some of their attention and learn about this other practice. And that's the most important thing for collaborating. And okay. And I think that when you're a mathematician like me, one of the important questions to ask is, what do you think is holding you up? You know, I don't think very often people are open to. I want to come in here and use my technique. They're open to. I see that you can't compute problems as large or as fast or as scalably or as accurately as you want, and I have a tool that could maybe change that. That's a welcome argument. I'm just finishing. I'll just be 2 minutes. So it's quite a common belief that there's not enough software engineering in numerical software. Uh, I think I would qualify that. I think the best numerical libraries have the best software engineering. I mean, as much as we know how to do, that's present in these libraries. But there are many scientific libraries that have very little in the way of that. So I think it's one of these 90-10 sort of divisions. 10% of the libraries really do the best things, and 90% of them don't. Now, the other related thing is that like any social phenomena, the 90-10 applies to use of scientific libraries. 10% of the libraries are used 90% of the time, I think. There's a long tail of libraries with very few users, and so the effort to do the things is just not put into that. I think contributing to this, though, too, is the fact that the reward structures for um, you know dealing with software are not correctly oriented yet. There's perverse incentives, right now, and that'll change as we turn over generations and people who have to use software every day for their research realize that it's important and the engineering of it is important, but it's going to take a while. So unfortunately, I have another meeting, But I really liked giving this. Thanks for coming. And if you feel like mailing any questions to me, that's fine, and I'll do my best to answer them. And thanks, Letitia. Do you mind if I sign off now?
No, go ahead. Thank you very much, and thank you all for attending.
No, go ahead. Thank you very much, and thank you all for attending. Thanks.